How many different ways can you reach your destination in a grid, no matter the twists and turns? Unique Paths is a Pattern Mastery 100 dynamic programming classic and a favorite at Google, Meta, and Amazon. Over 30% of candidates make mistakes with state transitions or grid boundaries. Master this and you'll unlock the foundation for nearly every grid-based DP problem in interviews. Let's solve unique paths using the basic approach, so you'll confidently tackle any path-counting DP challenge. Given an MXN grid, count the number of unique paths from the top left corner to the bottom right corner. You can only move right or down at each step. Integers m, n, grid dimensions. Integer, number of unique paths. Picture planning a robot's moves through a warehouse, or a delivery drone's flight plan over a grid city. Interviewers might ask, how would you count all possible routes if movement is restricted to right and down? What's tricky? You can't move diagonally or backward. Many candidates overcomplicate or forget edge cases for the first row/column. Dynamic programming and combinatorics both provide solutions. The robot can only arrive at a cell from above or left. For any cell, I, j, the number of ways to reach it is the sum of the ways to reach I1, j, and I, j1. Initialize the first row and first column to 1, only one way to reach each cell along the edge. Initialize a DP table of size MXN, fill first row and column with 1. For each cell not on the edge, dpij equals dpi1j plus dpij1. Return dpm1n1. Solution 1. 2D DP Grid Time Complexity, OMN. We begin by defining a class named Solution. This simply organizes our method neatly in one place. This defines our function unique paths, which calculates how many different ways a robot can move from the top left corner to the bottom right corner of an m by n grid. The robot is only allowed to move right or down. Here we create a 2D grid called DP with m rows and n columns, and we fill every cell with 1. Why 1? Because the entire first row and first column each have only one way to reach them, the robot can only come straight from one direction. This grid will store the number of unique paths to reach every square. Creating this grid takes om times n time. We now loop through the grid starting from the second row. The first row already has correct values, so we skip it. Inside that loop, we loop through each column starting from the second column. Again, the first column is already handled automatically, so we begin from j equals 1. This is the heart of the algorithm. The number of ways to reach cell, I, j, is the sum of the number of ways to reach the cell above it, dpi, 1j. The number of ways to reach the cell to the left of it, dpij, 1. Because the robot can only move down or right, these are the only two ways to arrive at I, j. Finally, we return the value in the bottom right corner of the grid. That cell contains the total number of unique paths from start to finish. Final wrap-up. And that's how this algorithm works. It first initializes a grid where the first row and column represent paths with only one direction, then fills in the rest of the grid using the idea that each cell combines paths from above and from the left. Efficient, simple, and elegant. Test case check. Unique paths using dynamic programming. Let's test our function using this input. M equals 3 and n equals 7. These numbers represent a grid with 3 rows and 7 columns, and we want to count how many unique ways a robot can move from the top left corner to the bottom right corner, moving only right or down. Here's why the solution works. We create a DP table where each cell dpij represents the number of unique paths to reach that position. The first row is all ones because you can only move right. The first column is all ones because you can only move down. Every other cell is the sum of the paths from the top and from the left. And that's exactly what our program outputs, 28. This matches the expected result, confirming that the DP grid was built correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all unique paths through the grid using dynamic programming, efficient, accurate, and reliable. Solution 2. Combinatorial Formula Time Complexity, OM plus n. We start by defining a class called Solution, which simply organizes our method nicely. This defines the function unique paths, which calculates how many different ways a robot can travel from the top left to the bottom right of an m by n grid. Here we compute the total number of moves the robot must make. To reach the bottom right corner, it must move m, 1 steps down, n, 1 steps right. Adding them together gives us m plus n, 2 total moves. We choose the smaller of the two required directions. Either the number of downward moves or rightward moves. Why the smaller one? Because when computing combinations, C total, K, is symmetrical, choosing fewer items keeps our loop fast and efficient. This optimization helps keep the time complexity OM plus N. We set up a variable res to store the running result of our combination formula. Think of it as our accumulator. We now enter a loop to compute the combination formula C total, K, using a multiplicative approach. This avoids calculating giant factorials and prevents overflow issues. The loop runs K times, which is at most min M, N, keeping things very efficient. This line applies the combination formula step by step. We multiply by the next numerator term, then divide by the current denominator term. In simpler terms, we're gradually building C total, K, equals total K, total K, without ever computing the full factorials. This keeps things fast and safe in Python. And finally, we return res, which now contains the total number of unique paths the robot can take. Final wrap-up. And that's how this algorithm works. It first converts the grid walking problem into a simple combination formula, then builds that combination efficiently using a short loop. Efficient, simple, and elegant. Test case check, unique paths using combinatorics. Let's test our function using this input. M equals 3 and N equals 2. These numbers represent a grid with 3 rows and 2 columns, and we want to know how many unique paths lead from the top left corner to the bottom right corner, moving only down or right. Here's why the solution works. To reach the bottom right cell, the robot must make M, 1 equals 2 downward moves. N, 1 equals 1 rightward move. So the path is simply a combination of these moves. In total, the robot makes 2 plus 1 equals 3 moves, and we choose where the downward moves occur. And that's exactly what our program outputs, 3. This confirms that the combinatorial formula is computed correctly and matches the expected answer. Wrap up. So, our implementation is correct. The algorithm successfully uses combinations to calculate the number of unique grid paths, efficient, accurate, and reliable. Unique paths. Let's do a recap. So, we've just solved one of the most foundational dynamic programming challenges, unique paths. This problem isn't just about counting roots in a grid, it's about understanding how small decisions stack up into bigger patterns, a key skill that powers most grid-based DP problems you'll see in interviews. Breakdown recap. Conceptually, the task is simple. Find how many ways a robot can travel from the top left to the bottom right corner of a grid, moving only right or down. Every path you count builds from these 2 possible moves, and our goal is to track them systematically. Assess recap. We realized brute force would explode in complexity, so dynamic programming was the smart approach. The key insight was that every one cell's number of paths depends on just 2 previous cells, the one above it and the one to its left. Once we got that recurrence relation down, the problem became straightforward. Structure recap. We planned it like this. Start with a grid of path counts, initialize the first row and first column to 1 since there's only one way to move along the edges, and then fill the rest by summing the top and left cells. That pattern continues until the destination cell gives us the total number of paths. Implement recap. We implemented the logic cleanly, ran the solution on LeetCode, and everything executed perfectly. No syntax issues, no boundary errors. The DP table built up exactly as expected, and the output matched every test case. Check recap. After running multiple scenarios, all test cases passed successfully. The results lined up perfectly, even for edge cases like single row or single column grids. The logic worked efficiently and consistently. Closing insight. The big takeaway? Unique paths teaches the foundation of dynamic programming, breaking big problems into overlapping subproblems. Once you master this pattern, you'll start seeing the same logic in everything from grid traversal to robot movement to advanced combinatorial DP questions.